Good day again, Evan Snyman for Umechluko, Making a Difference. We're now going to look at the third lesson on Euclidean geometry. We're looking at the converse of the proportion theorem. Sometimes it is also called the intercept theorem. Now, a basic principle always in mathematics is that if you can get from London to New York, you should be able to get from New York back to London. So in the original proportion theorem, we said that if one side was cut by a line that is parallel to the third side of the triangle, it ended up with the other line also being cut in proportion. Well, the converse of this says effectively the same truth but in reverse. That if I started out with two sides that were cut in proportion, such that this was, for example, 10 and 4, and this was 15 and 6, well, again, if I started out two fifths or a third of the way along a swimming pool or field, and I ended up on the far side of the field 2/5 of the way along or a third of the way along, if I started in the same position and I ended up in the same position and I'd run across in a straight line, hopefully you'd realize that I must have run across in a manner that was parallel to the other side of the field. And so what this theorem now says is that if the two sides were in proportion, then it must follow that the line was parallel to the base of the triangle, or to the third side of the triangle. And so what we're going to look at here is a situation of trying to now use this in a variety of examples and proofs. Again, please note that the reason for this is sides in proportion. Okay, what I've now gone and done is I've gone and found 3 different questions from past exam papers, and here is one from the Siavula textbook, and it says, cool, I'm given a triangle STU, VW is parallel to TU. Yes, I can see that on the diagram marked over there, that these two things are parallel, and it tells me that WVT is equal to TVU. So I can see here they've marked these little dots that these two angles are equal. I'm told that SW is 10 and WT is 20, and I'm being asked to find out the length of SV. How long is the line SV? Well, let's work it out. Okay, so what do I know? I know that these two lines are parallel. Parallel lines normally lead to co-interior angles or corresponding angles, alternate angles, but that is very much a position from grade 8. It does not mean to say that it does not apply in our current diagram. However, what I do want us to focus on is that now in grade 12, parallel lines should lead us to think along the lines of that the sides will be in proportion. So let's have a look. My problem that I have right now is I've got no information about this right-hand side of the thing. I've got no information about either the full length or any of the part lengths of this line on the top right-hand side. So neither SV nor VU nor SU are known to me. So I cannot proceed by immediately saying I know something about the proportion. I will first need to find out one of the pieces of this, one of the pieces on this right-hand side of this blue line SU. To that end, I'm going to go back a step and say what I said to start with. In grade 8, parallel lines made me think of co-interior, corresponding, and alternate. And what I have in this situation is I can see, hopefully, that these angles here are alternate to one another. So that means that this angle here is the same size as the two angles that I measured earlier on in green. The advantage of doing that is that means that this lower right triangle is now isosceles. And being isosceles means that if this angle is 35, if this side length is 35, that this side length over here is also going to be 35. I now have achieved my goal. I know one of the pieces of the line length SU, and as a result, I can calculate the other pieces if needed. Now, what I'm going to do is I'm going to try and write down my argument the exact same way that I've just discussed it with you. Because after all I'm doing is writing down what I've just said in words. I'm having an argument with you, a discussion with you to lead from one step to the next. So, my proof is going to be as follows. Okay, we said firstly that WVT equaled angle VTU, alternate angles on parallel lines. WV was parallel to TU. We said that meant that therefore triangle VTU was isosceles with the two angles equal, okay, base angles equal. And as a result, we said therefore that TU had to equal VU. Okay, well, we now know not just that they're equal, but more specifically, since they told us how long TU was, we know that VU must be 35. Well, again, that allows me to work out SV, because I know that because these sides are in proportion, because these two sides were parallel, I know the sides are in proportion. So I know that SW over WT must equal SV over VU. How do I know that? Because the line was parallel to the third side of the triangle. So it's the proportion theorem. Okay, and again, I can abbreviate it down to prop theorem. Okay, and as a result, I know, and the reason I know this is the case is because VW was parallel to TU. Now, what I'm going to do is I'm going to substitute all my values back in here. And so I'm going to, unfortunately, I've run out of space here for the moment. So what I'm going to do is I'm going to continue my argument over here on the right-hand side. And so I'm going to simply substitute all my values in here. 10 over 20 equals SV, the side I'm looking for, over 35. And I think you'll agree that if I was to cross multiply, I would get that SV equaled 17.5 units. 17.5 units. Now please note, I don't know that it's centimeters, I don't know that it's inches. They haven't given me any units in this particular question, so I'm going to leave it as being 17.5 units. Please see how in this case I use the proportion theorem in its ordinary form. I have not gone and used the converse, I've simply gone and worked forwards with my theorem. What I'm now going to do is I'm going to look at a slightly more complicated example. And you'll see that in this case there are multiple sets of lines that are parallel to one another. And I think that here the skill is actually in trying to keep track of the various pieces of this diagram. So again, I'm going to go and make sure that I understand what it says here. It says to me that we have this triangle where the first pair of lines are parallel. I'm going to mark that in orange. HG is parallel to, and again, were we to have been back in grade 8, I would immediately jump to parallel lines means that I have alternate corresponding or co-interior angles in play. Now that we are sitting with the grade 12 theorems, we know that this means that sides are going to be in proportion. So I know that IJ in combination with HJ must be in proportion to IL in combination with GL. However, that's not all they told me. They also told me that KL is parallel to JG. So these are parallel. And so that tells me that this piece with regard to that piece is equal to that piece with regard to that piece. Now, I specifically have chosen not to label them this time because I was hoping you'd see it for yourselves, but both the orange and the green examples make reference to IL in combination with LG, which means that I can therefore link the green and the orange theorems, or the green and the orange pieces of knowledge, to one another by this idea. So what I'm going to do now is I'm going to go back to the actual theory, to the actual proof. I finished my reading, and I'm going to start looking at the actual proof. They told me that JK to KI is in the proportion 5:3. So I'm going to fold them in here, 5:3. Remembering that I'm not meaning that it's 5 units long and the other one is 3 units long, simply that they are in that proportion 5:3. Determine HJ to KI. Well, the nice thing is by doing this color coding thing is you can see that I've marked the 5 and the 3 over the green stripes. That means that the far side will also be in the proportion 5:3 over the green stripes. But as we said, the green stripes and the orange stripes have a connection with one another. GL and LI are in use in both situations, which means that I now know that the orange stripes are in proportion 5:3, which means that I now know that the HJ to JI is in the proportion 5:3, writing it over the color coding. That is what they asked me. Determine the length of HJ to KI. Now what I'd like you to see there is that I'm going to be doing 2 different steps, the same as I did with the previous example. The first was an argument with myself, where I've written down almost haphazardly, some might say, but it isn't, it's been structured to my argument. But I've written down how I thought to myself, and now what I'm going to do is I'm going to explain that thinking to the third party, to the person who's marking my work. As I said, someone with whom I can't argue, so I'm going to write down all my statements. So, if I know that JK to KI is in the ratio of 5:3, that will also be equal to the length of GL to LI, or the proportion of GL to LI. Why? Because the proportion theorem with KL being parallel to GJ. JG. Okay, that was the green piece of information that we used earlier. But I know that GL to LI equals 5:3, also equals HJ to KI, because of the proportion theorem, in this case, HG being parallel to JI. So in the first case, I've gone and used the green theorem, even though they initially talked about it second. I was using it here first, and then for the second part of my argument, I was using the orange statement. Now, I don't know about you, but me, I find that this color coding helps a lot in keeping track of my own thoughts, and if I can keep track of my own thoughts, it will then help me guide my argument as I try to write it down for the examiner or exam or test purposes. So I would strongly encourage you to use this idea. Okay, now, admittedly, this third lecture was entitled The Converse of the Theorem, and you might want to comment that both of these are using the original theorem. So what I'm going to do now is look at the only example, and believe it or not, this is the only example I could find that used the converse of the proportion theorem. Now, again, what you'll notice is that it is a diagram where no sides have been marked as being parallel. Okay, you have been given the lengths of a bunch of sides, but no sides have actually been marked as parallel, even though it does appear that there is definitely one pair of sides in that diagram that look as though they are going to be parallel to one another. And so what I'm going to do here is, again, do some thinking about proportion. And so before I write down any proof, I'm going to do some thinking, even so, as I said, where I'm trying to explain things to myself. And so the first thing I'm going to look at is this idea, as you said previously, of side to side, leading to side to whole. And again, if this is 12 and this is 36, I could see this as being the entire length here as being 48. And as a result, I should be able to see, well, hold on, 12 over 48 is in the ratio of 1:4, or alternatively, 36 to 48 is in the ratio of 3:4. Either way, what I'm hoping to realize is that the proportion, not saying the length, because we know that the lengths are 12 and 36, but that the proportion of these pieces is 1:4. 1:3, sorry, I apologize for that. 1:3 parts to part, or 1:4 parts to whole. If I now take my gaze over to the right, to the bottom right, if this is 20 and this length is 80, we can see again that this is in the proportion 1:4, which means that this missing piece here would be in the proportion of 3:4. Again, I am quite aware that the length of the side here would be 60. I'm not talking about the actual length, the physical length, I'm talking about the proportion. And again, this is one of the things which many kids struggle with, is we are not talking about lengths, we are talking about the ratio, which is the fraction between two sides. So again, what I've got here in orange and green is a situation where hopefully you can see quite clearly that the left-hand ratio, 1:3, and the right-hand ratio, 1:3, are equal to each other. If these two things are equal to each other, then the converse of the proportion theorem says that as a result, we should be able to realize that this length here will be parallel, this side here will be parallel to this side here. And we now have our first question solved, that these sides are parallel to one another, or these lengths are parallel to one another. Okay, so like I said, what we need to do is we need to write this down. And so for 9.1, I'm going to do exactly that. We can see that CT over CA equals 12 over 48 equals 1/4. And we can see that SR over SA equals 20 over 80 equals 1:4. Therefore, we know that SC is parallel to RT. Okay, because the sides are in proportion. So 9.1 is done. 9.2 requires us to now go further. It is further given that AR is 2/3 of RB, and BC is equal to 2x, and CD equals 1/2 x plus 1. They seem to be having a bit of fun here with bringing fractions into this question, but we are matrix for a reason. We can cope with this. So we know that BC is 2x, and we know that CD is equal to 1/2 x plus 1, and we are told that AR, hold on, let's think that one through. If AR is 2/3 of BC, if we know that AR equals 2/3 of BC, sorry, of RB, apologize, then we can see that we can rewrite this as being that AR over RB is in the ratio of 2:3. Again, the proportion means that we've got equal fractions. So we know that, again, this piece here, let's go use again a third color. Okay, so let's go and use, we haven't used red yet. So we are told that AR to RB is in the ratio 2:3. And they're asking us to therefore make some conclusion about the blue proportion on the right-hand side, given that we only have one pair of parallel sides in this diagram. So let's go through our argument. If we know that this piece here, AR, is 2, we can realize that therefore RB must be 90 centimeters long, 90 millimeters long. As a result, it must follow that therefore SB must be 70 millimeters long, because we know that our SR is 20 given to us. Well, now we have two sides of a triangle cut in proportion. In this case, 20:70, so in the proportion 2:7. So we can now write down our statement. SB over RS is 70/20, but it will equal BC over CD, which equals, BC was given to us as 2x, and the other one was a half x plus 1. And as a result, we can get that therefore 70 times a half x plus 1 equals 20 times 2x. And as a result, 35x plus 70 equals 40x. 35x. And as a result, 70 equals 5x, and as a result we get that 14 equals x, and we have calculated the value of x. I do apologize about this, the notation going across the page, and obviously in exams you would write this in a structured argument, one beneath the other. I hope you have seen how these pieces of knowledge, the proportion theorem and the converse of the proportion theorem, allow us to expand our abilities to work within triangles, and that the matric skill is to no longer see parallel lines as leading to corresponding alternate and co-interior angles, but now leading to the idea of sides being in proportion, and its converse, that if the sides are in proportion, that the sides must then be parallel. Thank you for listening into this chat. We'll move on to lecture 4 shortly.